Let's take a look at an alternative to the washer method for determining the volume of a solid of revolution. And this is called the cylindrical shell method. And let's draw a picture of what's going on. So let's suppose we have, in the xy plane, we have some vertical axis of revolution. And we have a region that we would like to rotate around. So it would look something like this, very roughly speaking. You have two copies of the same region on both sides. And it's being rotated around this axis of revolution. And you can kind of see how we have this washer right here. But what I would like to do instead is consider what happens if, instead of fixing a y value and looking at the washer that appears when you rotate around, what happens if you fix an x value instead? So over here in my original region, I'll identify the leftmost and rightmost x values for this particular region, and I'll just pick an x somewhere in the middle. And when doing either the washer or the cylindrical shell method, it's always nice to draw this vertical line segment above your picked x or y value. And the reason why we want to draw that is we want to consider what would happen if that line segment was rotated around the axis by itself. So it has its partner over here. And we can see how, if we were to rotate it around, we get a circle on the top, we get a circle on the bottom, we get a circle for any point on the line segment. And lo and behold, our cross section is a cylinder. It's the lateral surface of a cylinder. Now, that's different than if I had picked a y value, because then I would have gotten the washer right here. So it's important to keep track of if you have a vertical or a horizontal axis, because that will change whether you have cylindrical shell or a washer cross section determined by your y or your x value. So we already know how to do the washer method. So how are we going to do the cylindrical shell method? Well, it's still the same base theorem, the fact that volume is the integral of area. So we need to determine, instead of the area of the washer, we need to determine the area of a cylindrical shell. And the way we do that is we say, well, what would happen if I took this cylindrical shell and laid it out flat? So what I've done is I've cut along an edge of the cylindrical shell and rolled it out flat into the plane. All right, so this came from a cylinder right here, but we cut down an edge and then we laid it out into the plane. So what would be the area? Well, obviously it's a rectangle, so it would just be the base times the height. So the height is going to depend on the x, and it's right here in the picture. Here's the height. It's the distance from the bottom point to the top point of that region. And then we'd have the base. Well, the base comes from this circle. So really the base is a circumference of the circle. And remember, circles have circumference 2 pi times the radius, or pi times diameter, which is the same as 2 pi times the radius. But the radius is going to depend on the x value. And we can see here that that's going to be the distance from the axis out to the x value. So there's my radius in the picture. It's the distance from the axis to the x value. So once I put those two together, the area is going to be 2 pi rx hx, and that is my formula. Integrate from a to b, where a is the leftmost and b is the rightmost x value of the region, 2 pi r of x h of x with respect to x. And that's the cylindrical shell method. Let's take a look at an example. We're going to find the volume of the solid of revolution. Obtained by rotating the region bounded by y is equal to 0, x is equal to 1, and y is equal to the square root of x. And we're going to rotate that around the axis. X is equal to -1. And it doesn't really say whether we're going to use washer method or cylindrical shell method. In fact, you could solve this using either method. But let's go ahead and just sketch it out and see what this would look like. Start by sketching the region. Y is equal to 0. So here's y is equal to 0. X is equal to 1. It'll be this vertical line here. And then y is equal to the square root of x is a half parabola. So here's my region. It's kind of a rough picture, so let me clean that up. I'll draw a new picture. And what's important is we have the region. Here's 1, here's 0. This would be a height of 1 right here. And we're rotating this around the line. X is equal to -1. So that's my axis right here. Now, whether you are using cylindrical shell or washer method depends on whether you're considering x values or y values. And remember, if the washer method, we learned that if we have a vertical axis, to use the washer method, we would have to pick a y value. Pick a y value, we get this washer right here. And you could do the problem that way, but let's see what would happen if we picked an x value instead and used cylindrical shell. Okay, so we notice we have the leftmost x value 0, the rightmost x value 1, and we'll pick an x value here in the middle and draw the vertical line passing through the region. And if we were to rotate this, we would see that we do have a cylindrical shell cross-section. So we need to determine two pieces of information about the cylindrical shell. We need to know the height of that cylindrical shell. So here's the height. We also need to know the radius, the distance from the axis out to the x value. So there's my height from top to bottom here. The radius is the distance from the axis to the x value. Now for cylindrical shell method, radius is usually very easy. It's just a matter of taking x plus or minus the axis value. This axis has value x is equal to -1. So of course we know that this is x here. We know that this distance is 1. Distance from the y-axis to x is -1 would be 1. So my radius is going to be x plus 1. And that's pretty straightforward. The height isn't too difficult either. I noticed that, hey, I just want to know the distance from the x-axis up to the point. The point is on the curve. Y is equal to the square root of x. And so I want the vertical distance, the y distance, which is root x. As soon as I have my radius and my height, I can just plug it all into the formula. So the formula is volume is the integral from, we're going from the leftmost to the rightmost x value, 0 to 1, times, integrate the area, which is, for a cylindrical shell, 2 pi radius. My radius is x plus 1, times the height is the square root of x dx. Oops. So now we just need to evaluate this integral. And to evaluate this integral, we'll just want to distribute out everything. In fact, you can always take that 2 pi on the outside if you want as well. So we could write that as 2 pi integral from 0 to 1. I've got an x times a root x, that's x to the 3/2, plus 1 times root x is x to the 1/2. So we have 2 pi, and we'll add 1 to the power. 5/2, divide by 5/2, which is the same as multiplying by 2/5. Here we'll get the same thing with 2/3, x to the 3/2. Evaluated from 0 to 1. So 2 pi. If we plug in 1s, we get 2/5 plus 2/3. Plug in zeros, we do get 0 plus 0. So scratch all that out. And then common denominator. So I've got 2 pi times 15, that would be multiply the top and bottom here by 3, top and bottom here by 10. So I've got 16 times 2 is 32 pi over 15. And that's exactly the same that you would get if you went back and used the washer method instead, and you can check that.